Welcome to Lecture 28, entitled Stokes Theorem. And so here we're going to be looking at an application in 3D. This lecture basically is covered in material from reading assignment 5, that's sections 4.2, which deal with cylindrical geometries, section 4.6, and additional problems in section 6. The objectives here are to apply the Stokes theorem for magnetostatic problems. And the concepts and visualization skills are determining the direction of the field and the functional dependency of the field's magnitude, and developing the procedure for determining the field for a cylindrical symmetry example. As usual, the second slide is just an outline of the slides to follow, so we'll just skip over this slide. Okay, so I'm going to use a magnetostatic example. This is for a source-free field. And so these are going to be basically fields which are homogeneous, involving homogeneous media. And so that just means that these are constant values and don't depend on position. So we can either describe this problem in terms of a magnetic field or a magnetic flux density. If we describe it in terms of magnetic field, then we have one equation with a curl, one with a divergence, with a J subscript E. This is a current flux density, or we could express in terms of the magnetic flux density, in which case would be curl of B equals mu times JV, which is the current flux density, and divergence B is equal to 0. In our case, basically, we're going to work with the H version, which means we're just going to let H be equal to F to just sort of have a consistent set of symbols. And we're going to just let J of subscript E just be J. So this will be a current flux density. F in this case will represent the magnetic field. And so if we take this nomenclature and then apply Stokes theorem, then effectively on the left-hand side, this is a closed contour integral. And this is related to taking the curl of the vector field times the dot product of a differential surface area vector enclosed by this contour. So the surface area can take on any shape. In fact, it's advantageous because we can then choose the surface area and the curl of a vector field to be more or less in the same direction, so as to make this computation as simple as possible. Now, the curl in this case is equal to J, so that means we can just replace this by J, and given that J is a given, means that the right-hand side is the part that we'll be doing, where we do the real calculations. And the left-hand side will basically, we're hoping to somehow extract F out so that we can compute the value of F. And so symmetry will allow us to do that. So the problem statement we'll use here is to consider a cylindrical rod of infinite length with radius capital R and its axis of symmetry aligned with the z-axis. And the rod has the following current flux density distribution. For 0 is less than R is less than capital R, the field basically, the current flux density is pointing in the z-hat direction, and J0 is a constant value. Once you get outside of R, capital R, then there is no current flux density. And again, it would be in the z-hat direction. Again, R is the square root of x squared plus y squared. So this, given that it's cylindrical symmetry we're going to be dealing with, and we just choose to basically express everything in terms of cylindrical coordinates. All right, so what's the calculation procedure to compute F? Well, it's very similar to what we did when we looked at calculating problems in which we were dealing with irrotational fields. The only difference is you apply Stokes theorems rather than the divergence theorem. So the first step is to determine the nature of the symmetry and determine if you need to use superposition. Second is to establish the form of F and establish the shape of the closed contour. Thirdly, compute the left-hand side of Stokes theorem, then the right-hand side of Stokes theorem, and then finally equate the left-hand side and right-hand side to compute the value of the vector field F. Note, the procedure here is almost identical to problems that invoke the divergence theorem. All that changes is that the choice of an open surface, which is bounded by a closed contour. And so now we're dealing with surfaces, open surfaces and closed contours, whereas before with the divergence theorem, we were dealing with closed surfaces, and we're talking about bounded volumes. All right, so the first part of the solution to the problem is to establish the symmetry and also the need for superposition. And so what I have here is an interactive simulation, help you to understand the symmetry and to get some sense as to what the field direction would be and what the field magnitude depends on in terms of coordinates variables. So let's go through what this diagram represents. So this is just, say, a shell, and on this shell basically a current would be flowing. And so what we do is we take two filaments of current, one on this side of the shell, one exactly on the opposite side. So these two form a pair of filaments with a current flux density flowing through them. And we basically have drawn here a circle which is centered on the axis of symmetry. And I've placed an observation point here. And this observation point, the distance between this current filament and the observation point, and between this current filament and observation point are the same. All right, so that's basically the situation we've got. So what we would like to do is two things. One is to essentially say, well, let's take this filament and move it along this surface so that it sits here. But in doing so, we also do the same thing with this one and bring it over here. In that case, the distance between the filament and the observation point and the filament and the observation point, basically those two are equal in length. The distance will of course change, but they are essentially the same. And you can do that for all possible combinations of pairs so that you more or less cover this whole surface. You could do this for additional cylindrical surfaces of different radii, and you would end up more or less with the same picture. The key point to realize is that when you compute the field for this current filament using the right-hand rule, then what you'll find is that the thumb has to point in the direction of the current flux density, and the fingers point in the direction of the field, which would be in this direction due to this current flux density, and this direction due to this current flux density. But the total current flux density is the sum of these two, which happens to be this red one that you see here, and that is tangential to the circle at this point. Now, we can move these, as I said, this one slightly in this direction, this one slightly in this direction. What we'll find is when we do the summation of the two, we still end up with a field that's pointing in this direction. So one thing is clear, for all combinations of filaments, it's in this direction. Now, next possibility would be to essentially say, well, let's move over to a different location on this particular circle and repeat the same experiment where effectively now we move these two lines around such that the distance between this and this observation and this observation point basically is the same. We end up basically with the same results. So what it says essentially is that the field at each point along this circle will remain the same. In other words, it's uniform, and it's tangential to this circular line. So these sliders allow you to play with this object. So for instance, slider 2, it's just a blue observation point on expanding red circular ring. So what it allows you to do is increase the radius of the ring, and the blue point moves with it. Slider S is selecting different current flux density pairs on the circumference of the blue cylindrical shell that are equidistant with respect to observation point on the red circular ring. So this basically just means that you're moving one in this direction, one in this direction, and the last one is where you're moving this one around in this direction and this one around in this direction, and the observation point is essentially moved with it. So that more or less tells us that the magnitude of the field will depend only on the radial direction. We don't know what that dependency is yet, and that the direction is going to be either in this tangent to this circle here, which is in the theta hat direction. If this current were in the flux density were in the opposite direction, then the field would be pointing in the opposite direction, which would be the minus theta hat direction. All right, so based on that information, we can write that the field has this particular form. This is a unit vector, and this basically represents that it's dependent on the radial distance from the axis of symmetry. And so there are two different options that can exist. One is if this magnitude is greater than or equal to 0, then this will be just the magnitude times theta hat. On the other hand, basically, you can have a situation where the field's in the opposite direction. Magnitude is still the magnitude. And so the direction was determined by just multiplying this through by -1, so this becomes positive and this becomes negative. Again, the right-hand rule basically will determine the direction of the field. So if J points in the Z direction, then F must be pointing in the theta hat direction. Just a word of warning, you should memorize the Cartesian form of the theta hat vector, which is the one that's shown here. Okay, now that we have a general idea as to what the form of the field vector is, we now have to create a closed contour, and that closed contour we associate with Stokes' theorem. And so there's some general criteria as to how to decide on what that closed contour should look like. And I've just stated them here in bullet form. The vector field F is parallel to the tangent vector on the contour segment, and the magnitude F is constant at each point on the same contour segment. Hence, F dot T ds is either the magnitude F ds or minus the magnitude F ds. And it means that magnitude F can come outside the integral. So that's one. Second option is the vector field F equals 0 on the contour segment, hence F dot T ds equals 0. Or thirdly, the vector field F is perpendicular to the unit tangent vector on the contour segment, in which case the dot product between F and T ds is equal to 0. So in our case, since we have an indication of what the field would look like, we're going to create a cylindrical contour with a variable radius r centered on the axis symmetry of the cylindrical rod. And so this is the left-hand side of Stokes' theorem, the field times the unit tangent vector ds. And the conditions we're looking at are either F is perpendicular to the tangent vector, F is parallel to the tangent vector, or F equals 0. So these are the cases that we're considering. All right. So let's set the problem up here, and this is just a visualization of the closed contour. We know the closed contour basically is going to be in a circular direction, and it's basically going to have a variable radius. And here's a diagram showing this infinitely long cylindrical rod, which is in gray. This gray basically is just a shadow. It's basically an extension of this circle that you see here. However, the real cylinder is the exterior circle that you see here. Within this circular region, you have a current flux density, which is uniform, shown in blue arrows, pointing in the z hat direction. All right. The contour basically can be adjusted, and so it has a radius r. The example I've shown here is where the contour happens to lie inside the conductor, but this could easily have been increased so it lies outside the conductor. In this diagram, what we're showing is that the area vector is pointing outwards, that is in the z hat direction. The current flux density, which is the black dots that you see here, is also out of the page. And the closed contour basically is in a counterclockwise direction. Right, so this is the red contour, and this is the area enclosed by that contour. When we talk about Stokes' theorem, we're only caring about the area enclosed by the contour. Now let's look at this from a right-hand rule perspective. If the tangent vector is in this direction, then by the right-hand rule, if the fingers point in the direction of the contour traversal, and the thumb points in the direction of the area vector, hence this dot shown here indicates that the area vector associated with this red region must be pointing also in the z hat direction. Now I've chosen the T ds to be in the same direction as the field. It doesn't have to be. Just makes everything simpler in the sense that you get positive quantities showing up. Anyway, this is a basic diagram that we'd be working with, and this is only showing for the case where the contour is inside, but we could have easily expanded outwards. Make a note that when we look at the right-hand side, we're talking about the total current enclosed, so we only care what's happening inside this red contour. We don't care what's happening outside of it. All right, so these are just the descriptions for this particular interactive diagram, which you can access at this link here. Okay, so we're going to now compute the left-hand side of Stokes' theorem. So this is just again summarizing by the right-hand rule. If the thumb points to the direction of the z hat, direction of ds, and the same direction as j, then the finger points in the direction of the unit vector t, which is counterclockwise in the xy plane. The field in our example points in the same direction as unit tangent vector t by the right-hand rule. Now, we could have chosen the thumb to point in the minus z hat direction, in which case the unit tangent vector t would have been clockwise. the direction of J would remain the same and F would still remain counterclockwise. You can work this out as an experiment if you wish. I chose it this way so that all dot products produce positive quantities. Okay, so my field takes on this. It's counterclockwise, you can see. And the radius basically is just the square root of x squared plus y squared. Okay, so I'm going to have to parameterize the contour. I need to know what TDS is. So basically we choose x to be r cosine theta, y equals r sine theta. Z is equal to 0 in this case. We're just basically on the xy plane. 0 is less than or equal to theta is less than or equal to 2 pi. And so r in this case will be just r cos theta sine theta 0. We need TDS, so next thing we have to do is take the derivative of r with respect to the parameterization variable, which is basically theta. So this just becomes minus r sine theta, r cos theta, 0. TDS will just be r dot d theta, and so this is the expression, and this in fact is counterclockwise by convention, so we don't have to multiply negative sign. We now basically have to also compute what the field is in cylindrical coordinates, based on the way we parameterize the contour. So x gets replaced by r cos theta, y gets replaced by r sine theta, and these are substituted in this expression to finally give us this expression for f. And so now we can go ahead and do the computation. We can substitute for f, we can substitute for TDS, and do the closed contour integration. All right, continuing from the last slide, we're now in the position to compute the left-hand side of Stokes' theorem, which is the closed contour integral of the field dot product, the unit tangent vector for the contour. And so in this case, we just collect the terms. Here's the field term. This is the tangent vector term. F of r basically is the scalar that we're trying to determine. It's a function of radius, but it can come outside the integral sign since it's not a function of theta. If you do the computation, we end up with 2 pi r f of r. Notice that this is a fixed entity, and essentially for any given geometry you do this calculation only once. And just to make things somewhat simple, I have basically compiled a table for the other types of symmetries that you're going to see. Planar being one, toroid, which is a donut, solenoidal, and cylindrical. And so I've given here, for instance, for planar geometry, it could be a slab or sheet of infinite extent. The field could be in the x-hat direction and the current flux density in the z-hat direction, or you could have a field in the y-hat direction and the current flux density in the x-hat. And this is another combination. There are other combinations as well, but we're just taking these for example. If we did the calculations for these, and on the left-hand side of Stokes' theorem, what we would find is that we get two segments making a contribution, and these would be exterior to the slab, one on top, one on bottom, or one on left or right, doesn't matter. And this x would be the length of the contour segment. Turns out that Fy1 and Fy2 would be the same. So effectively, you're only solving for one because these two are identical. So in fact, you get 2 times one of these units. For instance, for this situation, then we end up with this set of expressions. Again, this Fz2 will be equal to Fz1. So if basically we're taking the contour segments to be one on either side of the slab or sheet. And the last item, this would be in the case where we're dealing with a field in the z-hat direction, current flux density in the y-hat direction, similar situation. For the donut, we'd have a current flux density which encircles the donut. So if you were to look at a trace in the xy plane, you would see that J, the flux density, is either in the z-hat or minus z-hat direction, as basically the current spirals around. And F by the right-hand rule will be in the theta-hat direction. In this case, basically, we end up with the left-hand side just being 2 pi r f of r. R is the radius of any circle parallel to the xy plane and centered on the axis symmetry of the donut. And we have basically a solenoidal case where the current flux density in the theta-hat direction. In this case, we end up with 2 segments, one which is for r less than r, and we end up with the left-hand side being some constant times the length of the contour segment, and the other contour segment, which would be exterior to the solenoid, would end up with a value of 0. And lastly, the cylindrical case, which is the one we've just considered, is just basically summarized here. All right, these are just a couple of notes, just to mention that for the planar and solenoidal case, there were 2 contributions on the left-hand side. And second note is other combination of the direction of F in the planar case have not been mentioned. And thirdly, that the expressions above assume that the vector tangent to the contour traversal is in the same direction as the field. It doesn't have to be. It just means that when you take the dot product, you end up with a positive entity. All right, so now we do the computation of the right-hand side, which would be just to integrate the current flux density times the differential dot product with the differential surface area vector. Well, we've chosen the differential surface area vector to be exactly in the same direction as the J, so that make this as simple as possible to compute. And so we know what J is, but we have to be careful now because when integrating, we know we have a discontinuous function. So we have a region in which the current density was a constant and a region where it was zero. So we have to consider two cases. The first case is for radius less than capital R, which is the exterior perimeter radius of the cylinder in which a current flux density exists, and then exterior to that region. So in this case, J dot ds would be, and this we've just done in Cartesian coordinates, J is 0, 0, J naught, which is in the z hat direction, and NDS will be just 0, 0, 1 dy dx. This is basically pointing in the z-hat direction. This is the differential surface area vector. If you do the computation, the dot product, this is just j naught dy dx. This is in Cartesian coordinates. You're integrating over circles, so the upper bound would be r squared minus x squared. Lower bound is minus square root of r squared minus x squared. Value between r and minus r. So again, this is r is a free parameter, and that's valid up to a value of r equals r. And so we basically have written it out in this fashion. If you integrate this, it's just pi r squared j naught. So this was basically what the right-hand side would be for this region. And for the region greater than r, that means basically that you would be using the same expression, but r would be basically replaced by capital R, because for any r greater than r, there's no additional contribution to the integrand since j naught equals 0. So outside of r greater than, for r greater than r, the integral of the current flux density, which is basic of the over the surface area, which is just the current, would just involve this little r being replaced by capital R. And if you do this computation, this becomes pi r squared j naught. So these are the two different regions to consider. And here you can see, for instance, this is what the contour would look like for the case r greater than r. And you can see here it encapsulates the total current flux density. And of course, in this region, there is no current. So there's no contribution being made in this region, but you're encapsulating the total current just because of this area here. Here, we're only seeing a fraction of the total current. All right, so the last step is to equate the left-hand side with the right-hand side, and then compute the field F. So we have two regions to consider, and so it's a region from 0 to R, and the region that's greater than R. So here we basically have collected the left-hand side and the right-hand side. The left-hand side, of course, never changes for a given geometry, whereas the right-hand side is the part that's changing. So just using the information from the previous slide, we can just write left-hand side, right-hand side for this region, and left-hand side and right-hand side for this region. And so we're interested in what f of r is, so we can solve this equation, and we end up with an expression for f of r for 0 is less than equal to r is less than equal to capital R, as well as the condition when r is greater than r. And now we need to know what the vector form is. We know that the field points in the theta hat direction, so the field is just the magnitude times the field direction, and so we end up with the final result as being the field looking like this for the case 0 less than equal to r is less than equal to capital R, and r greater than capital R. Now sometimes it's convenient to make use of the expression in a slightly different way. If we were to integrate the current flux density over the full area or cross-section of the conductor, here basically we've just shown it in Cartesian coordinates, but could easily solve this in polar coordinates, then this is equivalent to pi r squared j naught in the event that j naught is basically just a constant value. And this by definition is the current flux, which is the total current that's flowing through the cylindrical rod. So we can therefore take j naught, express it in terms of I instead if we wish, because normally it's the current we measure, we don't measure current density. So that means we would take J naught expressed in terms of I, substitute into this expression, substitute in this expression, and the resulting expressions are the ones shown at the bottom of the slide. All right, so finally we'd like to graph the results. So this is just the magnitude. And so you can see for R less than R, it has a linear ramp. And we just use these specific values just for sake of illustration, J naught and R. And once you get R to R equals R, then beyond capital R, it has a 1 over R dependency. And so this is basically then gives us the whole, the field over the full region. All right, that concludes lecture 28. Thank you for listening.